All right, so it's my pleasure to introduce Professor Aldeida Aleti. She's an optimizer at Monash who doesn't live in the optimization group. In fact, she lives in even a different department. She's also an Optima CI now, and she's managed to do many interesting things over her career, won many awards, which I won't go through. But she's going to talk to us about how to optimize test cases for evaluating LLMs. So I think the interaction between LLMs and optimization is exciting space, very fast moving. So I'm very keen to hear what she has to say. Thanks very much, Aldeida.
Thanks, Peter, and thanks, everyone. Nice to see everyone. My background is in optimization and software engineering and also AI. So the kind of work that I do at the moment and what this talk is going to be about is how do we evaluate LLMs and how optimization can help us discover better test cases. I'm going to focus more on the problem than the algorithm. So, what is this optimization problem that we need to solve? I'll present some of the works we've done there. The optimization algorithms at the moment, they are quite naive, but there's an opportunity to do more in that area. So that's how my talk is going to be at the moment. So I think this problem of why LLMs need to be evaluated perhaps doesn't need a lot of motivation, but I'm just, I guess you've heard in the news now, LLMs, where they can get it wrong, they hallucinate, and they're being used more and more to perform critical tasks. But I wanted to bring you an example that just happened today to me, where I'm repairing my gutters, and I asked, the two tradies came and checked the gutters, and they sent me a quote, and they apparently they used this quote. What was generated by an LLM, and it's a formal quote where I'm supposed to pay more than $20,000, but as you can see there, clearly very sloppy, generated by an LLM. And as you can see there, well, there's like weathery with compliant box, the one on the top, new gutters in steel, Sinuther Pro C. So I don't know what that means. And, these, smaller businesses are using these LLMs more and more to help them, reduce, become a bit more efficient, reduce the work that, don't hire more people to create these quotes, and they use LLMs more and more, and they hallucinate. So the kind of problem we're trying to solve is, well, how do we properly evaluate these LLMs before they are used, in real world? Because in this case, it wasn't a safety critical situation. I guess it was sent to us and we had to check, but it's not a good look in a way. It's not professional. And of course, they're going to be used more and more, but how do we evaluate them? And probably you've heard also in the news where LLMs were used, for example, as chatbots, talking to customers, giving the wrong advice. There was this case of the airline that then got sued for the LLMs giving the wrong advice. So LLMs are being used more and more. How do we properly evaluate? How do we test them before they are deployed, and that we can detect these issues? I'll give you another example, which is where we've mainly focused with the works that I'm going to present to you, of vulnerability detectors. So LLMs are being used a lot in software engineering. Software engineering is the area that probably is most impacted by LLMs, so we probably have it as well, where LLMs are used at every stage of software development. And this example is with a vulnerability detector. As you can see, the code on the left contains a vulnerability, and the vulnerability is in line 7, I believe. And so the model says, well, this code is vulnerable, and the model confidence in that case is 99%. And so these kind of tools also produce, tell the developer, yes, it's vulnerable, but which lines are the ones that are contributing more to the vulnerability, that is, to the decision that this model is making in terms of this is vulnerable or not. And the contribution is the one on the right. And as you can see, the model is saying, well, the first line contributes 13%, And the line with the biggest contribution, as you can see here, is the one 27% that is just a log message. So really, there's no vulnerability there, but because it is using these terms of error and so on, those are often seen in vulnerable code as error messages, and so there are frequent things that are seen in vulnerable code, and hence the model, because of the high frequency, is thinking that those are relevant to the vulnerability, but they are not. So as you can see, although this tool is working well in terms of, it was correct to say that the code is vulnerable. It had a high model confidence, which is good, but it decided on unrelated parts of the code. So there's probably some spurious correlations there. It's or memorization that this LLM has done, that it's actually giving us the right answer, but not for the right reasons. I'm just going to stop a little bit here. I wanted to kind of see what people think. Why do you think this is a problem? Or where do you think this might be a problem? If, for example, we have a case like this, a vulnerability detector, that gives us the right answer, suppose that you're using this, and it's telling you this code is vulnerable, but it's kind of then it's highlighting the areas where it thinks it's vulnerable. And as a developer, why do you think this is an issue? I'm curious too, if anyone has some thoughts around this. Oh, Peter.
I mean, if then the developer looks at this and goes, oh, I'm going to fix line 4 or line 5, because clearly that's where the error is. And then they mark the thing as fine. Let's say even that maybe they rerun the vulnerability checker and it says it's okay now.
Yeah.
And problem solved, even though it was irrelevant, right?
Exactly. Yes, absolutely. That's the key thing. And so they're going to end up spending more time to figure out, what's happening. And another thing is, another issue that might arise is it's telling us the right answer, that because probably this model has seen similar bugs in the past, and so it's learned this kind of spurious correlations and memorized things. But when we deploy it in the real world and it's kind of exposed to a larger set of programs, it's more likely, that to get things wrong. So if we evaluate a model only using measures such as accuracy, recall, and precision, and it might have a high accuracy precision when we test it, not in production, but before we deploy the model, it might give us, good values in terms of accuracy and so on. But perhaps there might be some issues with overfitting or memorization or, spurious correlations. And then when we deploy it, then suddenly it's not working as well anymore. So it's important that we don't evaluate LLMs not only for these kind of traditional measures, machine learning measures, but we also look at deeper and look at their reasoning, look at their explanations, and look at why are they making those decisions, and are they truly trustworthy decisions? So I mentioned the word trustworthy, and so this is an area that I think it's becoming quite interesting for me, but it can mean very different things. And this is a paper that describes this was in the area of AI, broader AI, talking about the different dimensions of trustworthy. So when would we trust a model? And there's things around human values there. So we would trust the model when it aligns with human values, and things like safety, autonomy, sustainability, and other values. Privacy, again, it's a human value. Fairness, so we would trust the model more when it aligns with our values. But there's things around robustness, generalization. If a model is not robust, we wouldn't trust as much. Does it generalize to other problems? Transparency, is it transparent? Can we reproduce the results? And one of the dimensions is explainability. So can a model explain itself? And do those explanations make sense to the user? And this is the area that we, the works that I'm going to present, the two works that I'm going to present, I'm going to focus on these areas. So when a model explains itself, how can we determine that those explanations are consistent with the answer of the model, that those explanations actually make sense? Like in the case, my previous slide, these are explanations. The model is explaining itself, telling us that this line here that is highlighted with a darker shade has a bigger impact on the model's decision. That's how the model is making those decisions, because it's kind of basing those decisions on those tokens. And so when we look at that, then as humans, we can tell, well, do those explanations make sense? Are they really, aligned with the fact that that code is vulnerable? And, in this example, we saw that the biggest explanation, the explanation that had the highest contribution didn't quite make sense. So the model, there's something wrong with the model. And I think this aligns a little bit with us as humans as well. I mean, we're talking to another human or to our students. When we ask them, what solve the problem, they might solve the problem, but if they don't have the explanation, if they can't explain how they solved it, I as a lecturer, well, probably they don't understand it, or they haven't solved themselves. Maybe AI, they use AI. So explanations are very important in terms of trustworthiness, to determine whether an output is trustworthy or not. And actually, we wrote a paper on this with a focus on software engineering. So what does it mean for an AI software engineer to be trustworthy? And this is new ideas emerging results paper. So this talks about those dimensions that matter for software engineers, AI. We call them AI software engineers and not AI coding models, or because the future of software engineering is really, software engineers are going to collaborate with more coding agents that are not just doing coding, but they are doing other software engineering tasks like requirements and design, testing. So actually, the software engineering teams of the future will be humans and AI software engineers working together, and AI software agents working together. So here we were talking about what are those dimensions that matter in terms of trustworthiness. But also there's other work pointing out to this idea that actually explainability, and there's a lot here, so I can share the slides later. I won't go through all of these, but this other work highlighting the fact that a trustworthy system should give fair and reliable results along with its explanations. So explanations are important. And of course, this explainable AI has been, it's an area that has been there for some time. But this link to trustworthiness and link to human trust is an area that now it's kind of, there's some very interesting papers in this area at the moment, because there's a distinction between trustworthiness and trust. Trustworthiness is a system property, and trust is a human, I don't know, human. So it's a human thing, right? Mm-hmm. And sometimes we trust things that are not trustworthy. Mm-hmm. And sometimes we don't trust things that are. But in a way, trustworthiness helps to build trust. So if a system is continuously trustworthy, then we trust it more and more, right? But it doesn't mean that if a system is trustworthy, we're going to trust it by default, right? These are two separate things. So there's some very interesting work now looking at this, human aspect of trust and the system property of trustworthiness. But not a lot of work had been done in the software engineering space, like this, how do developers actually trust the outputs of AI, AI coding agent and so on. So now I'm going to talk a bit about some of the work that we've done this and how we have evaluated or generated test cases for evaluating trustworthiness with a focus on explainability. How do we know that these explanations are aligned? And because I guess we don't want, when I showed you those explanations, as humans, we kind of looked at that and it didn't make sense to us, right? But how can we do this automatically, especially if you're going to use optimization, automatically generate, test cases, and we need an objective function, right, to tell us how trustworthy is this system when we test with a particular test case. A test case in that example, for example, maybe let me go back a little bit. So if we're testing this vulnerability detector, a test case would be a piece of code that's buggy. And then the system would tell us, would produce an explanation, and the explanation would be this one. And then an objective function, or what we would need to calculate, a fitness function, which tells us, according to this explanation, how trustworthy is the system? Like, was it trustworthy or not? Is this a trustworthy explanation or not? And we looked at it. It made sense to us, but how can we automate it? How can we automatically tell whether these are irrelevant lines or not? So that's what the next piece of work we did. How can we define a fitness function that can automatically measure whether a test case, an explanation from an AI model was trustworthy or not? And so the example that I'm going to bring another example here, is when we use JIRA issue classifiers. So JIRA issue classifiers, so a developer can submit a JIRA issue, and then maybe that JIRA issue talks about a bug, or maybe it doesn't talk about a bug. So we want to classify whether a JIRA issue is about a bug or not, right? So there's JIRA issue classifiers. They're now currently used by developers to classify JIRA issues in terms of they're about a bug or not. And so these two examples, this is one JIRA issue, and this has been classified as it is actually about a bug. And this is another one that's, again, being classified as a bug. And both of them are correct. They're correctly being classified as containing a bug. But when we asked the model to tell us why did it classify it as a bug, as you can see, in this case, it uses these terms incorrectly. Incorrectly is a term that has had a big impact in the classification, and the term fail. And both of them, they're trustworthy because they relate to the fact that, the function failed. So they are tokens that make sense, and it's a trustworthy explanation. Whereas the second one is based on terms like a peer-checked cloudlet provider that has nothing to do with a bug, because this was kind of manually checked, and it's actually not an untrustworthy, classification. It's correct, but it's not trustworthy because the explanation doesn't make sense. So with this sort of piece of work, this is based on the idea that, well, what we can do here to automatically evaluate, we can take these keywords so in this case, I think we use different kinds of explanations. So LIME is one of them. And this example is when we use LIME to create those explanations. Given these explanations, what we can do automatically is look at the semantic relationship with the class, which is the correct class. So are they semantically related? And if they are semantically, and it's quite a simple method, really. If they are semantically related, then then it makes sense. Those explanations are trustworthy. But in this case, if they are not semantically related, then it doesn't make sense. But this method, like you could use something like a sign similarity that tells you, for example, in the case of how similar is the keyword incorrect with bug, the class bug, which is the class name. But so if you use cosine in this case, it doesn't quite work. You know, it's so initially we did try some simple things. It doesn't quite work. So somehow, okay, yeah, it doesn't quite work, the cosine similarity, because well, they could be, things could be not very semantically similar, but could be related. For example, is the case of, I somehow don't have this case here. Let me see. Yes, maybe I'll use this on this one. So it could be, for example, the case of computer and file are, you know, semantically similar, but the extension is not semantically similar, but it's related because it's a file extension. And these are, you know, semantically similar file and extension, but extension and computer are not semantically similar. So if the explanation returns the word extension, it doesn't find that it's semantically similar to computer, and so it will not consider it as semantically similar. So in a way, you know, in this paper, so my student Lam, what he was working on, and the paper link below if you want to know more about this, it developed this approach that looks at the relatedness, not just semantic similarity. And so creating this hierarchical clustering approach, again, not a very complex, very simple approach. But I guess the key intuition here is that semantic similarity alone doesn't work in terms of automatically classifying a prediction as untrustworthy. So we need to look at the relatedness. And this approach of using this hierarchical approach, which show, for example, in that case, you know, extension and file, they are semantically similar. And file is semantically similar to computer. So you can imagine, and I don't have this one, but you can imagine that you would have a hierarchy of computer, you know, similar to file and file similar to extension. Then computer becomes related to extension. And then, you know, this approach would classify extension as, you know, correct explanation for, you know, for a system that's, you know.
Did you use any particular semantic embedding for this?
Yes.
Finding similarity.
Yeah, I think yes. I think Lam did use an embedding approach, you know, to look at the similarity, and so that I don't remember now which one, but I think it is in the paper. But yes, we did use an embedding approach. Yeah, but by using that, then he creates this hierarchical clustering approach that, you know, then gives us the relatedness of how related things are. So that's, I guess, the whole approach, but I will not go in the interest of time, as I have a couple of more things to talk about. And, you know, if you want to know more about the data set, what I wanted to talk about is one interesting result here is that, so this graph here shows, so you probably, maybe some of you might be asking, well, model confidence, why can't we use model confidence? Because the model produces a confidence score when classifies something as, for example, in the case of an issue, the issue classifier case as bug or not, there was a model confidence, if you remember. It produces this prediction confidence, right? And this has quite a low prediction, quite a low confidence in both cases. So maybe prior work, they have used model confidence as, if the model is not confident, then maybe that's not trustworthy, right? Mm-hmm. And if we think also with humans, right? Sometimes if someone is confident, sometimes we tend to trust them more, maybe. But
it was louder.
louder. But actually, you know, when it comes to models, more confident actually doesn't mean that it's more trustworthy either. Because as you can see here, these tells us the number of predictions that were classified as untrustworthy. Sorry, that the model, I guess, was confident, and they were classified as untrustworthy, but they should have been, you know, like the model. So the model was confident about these, but they were actually untrustworthy, right? But it shouldn't be. The model should have not been confident. It's quite a high number, you know, considering. I mean, it's more than 10. It's quite a high number. It's not less than 10%, but a high number. And in this case, 198. And I guess even those other cases here, the model should not have been that confident about those either. And here, 198 cases where the model was 100% confident that they were trustworthy, but actually they were untrustworthy. So confidence and trustworthiness, you know, it's not, confidence is not a good measure, you know, to tell us how much we should trust the model. And I won't go through the results, but this is just one of them. You know, if we look at actually, if we use this approach, and Lam has called it TOKI, if we use this TOKI to tell us whether an explanation is trustworthy or not, and we use a human to actually label it, and if we look at how accurate TOKI was, it actually, you know, aligns pretty well with human labels, right? With what humans think is trustworthy or not. So these are the three different versions of TOKI, and the orange one is model confidence. In some cases, model confidence works well, but in some cases it's pretty low. But TOKI was consistently better. So let's go back to that was issue classifier. So that was with text. With text, we looked at semantic similarity. What about, let's go back to our first example, vulnerability detectors. How would we know, given these contribution scores, we can't use semantic similarity, right? I mean, it doesn't work. So how would we then automatically, and in a way, I guess I wanted to just perhaps remind us that what we're doing here, it's not optimization in Percepha. What we're doing here, we are defining an optimization problem, and later on we can automate and we can generate these test cases automatically. By, you know, at the moment we're selecting these test cases with a very simple random approach, but we can use more sophisticated methods to generate these test cases, and we are evaluating their fitness. We're defining a fitness function to evaluate them. So how would we do this for a vulnerability detector? And this is our other work. So I won't go into too much detail on this, but I'll explain the general idea of what we did. So basically what we want to do is, given these contribution scores, so it tells us that, well, line 27 here is relevant to this code being buggy or vulnerable. Sorry, not line 27, sorry, line 5. And this says a 27% contribution. And if we look at this line, I can automatically say that, well, this token and this token has nothing to do with where the vulnerability is. And this correctly tells us this line is vulnerable. So what this approach does, it has three parts, but I'm going to focus, I mean, the first part is creates this program dependence graph using abstract syntax. So basically, it creates, in a way, an a weighted program dependence graph, which is in a way a abstract syntax tree, where here would be, for example, each line and how they are connected. So for example, we've got an if statement, and within that if statement, I have another statement. So we can create this abstract syntax tree at different granularity levels. So basically, I then, by using that weighted program dependence graph, I can know how these lines are dependent. So I can know, for example, if these lines that my explanations are saying that are related to the bug, whether actually this node in my abstract tree is related to that node that is actually where the bug is. So what we can do then, we can look at this dependency level assessment, which is one of the components of this approach, which tells me, well, this is the vulnerable line, but this is what the model tells me why it has, why it has classified that line as buggy. It's using this node. And actually this node is connected, right? It's in the execution path. But if it said that this was the line, this other part, then it's not connected. So it's unrelated to the buggy line, right? Does that make sense? So we can use this weighted program dependency graph to give us automatically a label whether the explanation is trustworthy or not, based on is that actually connected, is that explanation connected to the vulnerability in the program dependency graph. But that wasn't, that's good and that produces good result, but what improves the approach even more is this second step, which is a set of previously known vulnerabilities that we can use to see, well, are these explanations related to these previous known vulnerabilities? So these are, code that we know, code snippets, not whole classes or whole, projects, but snippets of code that we know we've got this known set of vulnerabilities. And it's a very small machine learning approach, not an LLM or anything, something very quick that can tell us a quick answer whether this is related to previously seen vulnerabilities or not. And so this combination of these two parts tells us whether the explanation is trustworthy or not. I hope that made sense as a higher level explanation. But there's this paper that has been published that talks a bit more about the approach. And so that's any question about this one, or before I go to the next one that I wanted to talk about. So basically then we can use this one to sorry. Oh yes, Peter, yes.
I'm just wondering, it sounded like you knew what the vulnerable line was. What tool was telling you that? Or you didn't know what the vulnerable line was?
Yes. Did I do something? Where am I getting? I'm getting feedback. But I think we need a mic there. I'm not sure. Okay, now it's working. No, it's not. I'm using. Oh yes, sorry. Okay, yeah, thanks. Okay, it was my fault. Yes. So basically, this vulnerability detector tells us this is the vulnerable line, and it can be correct or it can be wrong. But that doesn't matter to us. Whether it's correct or not. What matters to us is whether the explanation is related to it or not, or is aligned with it or not. So okay. Yes, we do have, the vulnerable line that the vulnerability detector gives us, yes.
But isn't in your blue, not blue, the yellow block, which you labeled as machine learning part, yeah. Didn't you say that you have a kind of a database of kind of existing buggy code.
Yes, so that's from previous projects or, you know.
Yeah, so for that kind of set of code, you know where the bug is, right?
So that one is, so we don't, we don't know from that one, because that one is used to tell us whether these tokens that were highlighted, whether those were related to previous buggy code that were from other projects, you know, we've kind of downloaded lots of projects, and we've kind of extracted tokens that were, you know, we know that they have a vulnerability in them. And so then what we do is, well, if a vulnerability detector highlights parts of the code as contributing to the classification, and if that is not, you know, it hasn't been observed in the past, then it's less likely to be related to the bug.
Yeah, that's what I mean. You have a kind of history of, you already know this part of code or from previous project, you know they're vulnerable. And then you see this new code and you can map this new labeled vulnerable line to previously identified vulnerable line.
Does that make sense? So we've, as I said, I mean, I put optimizing test cases. We are, in a way, the optimization approaches, as I said, they have been quite, you know, we just select, you know, randomly select test cases. But what we can do here as future work is to be a bit more smarter in how we select these test cases, so that they are the ones that are more likely to reveal trustworthiness issues. And that's an area we're working on. So the optimization part is not there yet, but that's how do we choose? I think that's an interesting one. The next piece of work has some optimization, and that's the mortar, but I'll talk about this in high level just to introduce the problem. So this is about testing multi-turn LLM-based dialogue systems. I mean, like ChatGPT or, you know, Claude, or, you know, you ask them a question, it gives you an answer, and so you kind of, but it's not one turn. It's about the multi-turn. There's follow-up questions, and this is a different setting to single turn because there's context. And, you know, how do we test an LLM when there is, you know, you ask a question previously and there's that context that they need to carry to the next questions. So that's the setting here. And why we're doing it is because, you know, there's 63% of dialogues contain more than 2 rounds. And there was also some research showing that, which I'm curious to hear also with your own experience, how I think these LLMs have improved, but research showing that the more turns you have, these the errors accumulate in a way. And so if it starts to make an error for example, you ask them a question, it gives you the wrong answer, it's more likely to be more wrong in the follow-up questions than when that, you know, when you have, you know, ask them a question, it gives you the right answer, then, you know, they can continue to give the right answer. So there's this interesting behavior that researchers have observed with multi-turn LLMs, that these errors accumulate and these LLMs become worse and worse with more turns. So that's that was the setting here, and so basically, I guess it's again a test. It's dialogue system with questions and answers where you can ask. Things like how many kittens were there? And it's for who was in charge, Fluffy. So this who was in charge of follow-up question, there's some context there that is who was in charge of the kittens, right? Or who was in charge from the kittens. So there's that context that needs to be carried on. And in this paper, we do use metamorphic testing, and I'm not sure, have you heard about metamorphic testing? No? It's an interesting approach, actually developed by an Australian professor, at Swinburne University, T.Y. Chen, who also got the most influential paper award at ICSE, which is the top software engineering conference. So it's quite an influential technique. And with this, it's a very simple but beautiful idea, because when we are, again, it's this oracle problem, which all these works are about. So the oracle problem in testing is when we test a system, it can be AI-based, like an LLM, or it could be a traditional software system. The output, who says that, whether it's correct or not, right? That the system did the right thing. And so usually it's the human. And so if we want to optimize testing, how do we take the human out of the picture? And that's the oracle problem. So how do we build an oracle? And metamorphic testing addresses this by creating these metamorphic relations, which is we can create, when we have a test case, we can metamorphize it. We can kind of change it, the test case. And we define a relationship of how the output should change. If I change the input, the test case, in a particular way, how should the output change? So for example, if I'm testing a Google Maps application and I want to find the shortest route from A to B. And so the Google Maps return me a route. I don't know if it's the shortest, but if I take this B and I take it, it goes to a further location. When I sort of look at it from a bird's eye view, it's further, this B is further than the first test case. What do we expect the output to be? The shortest route shouldn't be shorter, right? Does that make sense? Because the location is further away. But actually there's been cases in Google Maps where even though, the location is said to be further away, then the shortest route becomes shorter because that initial shortest route wasn't actually the optimal one. So we can define these relationships. And if we look that this metamorphic relation is broken, then we can automatically say there's something wrong here. And we need to look, there's actually, I've discovered a bug in the system. Another example is, think of a self-driving car. If I'm driving, if I have a self-driving car and there's a stop sign, and then, the self-driving car stops. If I change the weather conditions, and I'm thinking about a simulation, right? Self-driving car simulation. If I change the night to day, or if I change the weather conditions, or if I change things that shouldn't impact that the car stops, actually I should observe the same behavior. And if that metamorphic relation is broken, then there's something wrong. And so this is what we're doing here as well. We're defining these metamorphic relations that are, in that case, we perform shuffling or moving questions or introducing new questions, or we're creating certain things in a dialogue. If I'm asking a set of questions, but if I change the order of questions without changing the context, I shouldn't receive very different answers, although there's some randomness, of course, in terms of, LLMs, they produce different answers, but they should, for example, if I ask, what is the capital of France? It should be Paris, independent of when I'm asking, the question. It should give me the same answer, right? And so the difficulty of designing this kind of approach is, how do we measure whether there is equivalent context, right? When I shuffle things or introduce new things, and I expect the answer to not change, but the context should have not changed either. Because if the context changes, then I should not expect, or if the context changes, maybe it's not relevant to the question. So measuring those aspects. And I think in this paper, a big part of the contribution was in this equivalent context checking. So I'm just talking about the general idea because I'd also like to leave some time for questions at the end, but that's this paper, if you're interested, I think, yes. So that's the paper that talks about how to do it. But I'm happy to talk about this offline as well. And the final thing I wanted to mention, and it's probably a lot that I've put in this talk, but another interesting problem in this space as well, we find these issues in LLMs, but what do we do then? How do we, so once we find these issues, what's next, right? If we, for example, discover that an LLM is producing vulnerable code, then what next? And so that my student Jan has been working on this problem of repairing LLMs or model editing or model repair. And there's some of his work there, which I think it's quite an interesting area as well. So this is one of the papers in code generation. So how do we, given a model, and this is an example here of the problem again. Given, for example, this model, this is the tokens, given K, so suppose that the model is producing the wrong next token, so that it's producing, in that case, it should be, instead of, it's producing K as the next token, but it should be H. So how can we then, change this? We can directly edit, the neurons to rank it higher because that's the right token. But the problem here, it should be simple, but it's not, because by changing the ranking directly, there is the risk of introducing side effects. So it might rank the right token for those test inputs, test cases that we want to fix. But then what we observe is that it introduces, it gives us the wrong tokens for other cases, introduces new bugs. And so that's the kind of work that Jan has been working on, and I'll explain more the high-level idea. There's a lot of text there. Please ignore the equations, but maybe just the figure. So the idea is to, so these are the different layers. So we want to change this next token prediction from, let me see, so the target is the blue, so we want it to be here. And the red, this is where it is, so we want to bring it here. So we want to change the response to the new target. But the work that Jan has been doing is, well, if we just change it to the exact expected token. So for example, so in certain cases, and this is actually, it's an optimization problem. So I think if this could be of interest. The idea is, for example, if I want to change, if it's giving me, let's think of, I'm thinking of fruit, for example. I'm trying to think of an example where you can have things that are semantically related, and it doesn't matter which of those semantically related tokens is produced. For example, it could be building, or it could be, what are different words for building? I can't think. Apartment, yeah, flat, and all of those are related, right? So it doesn't matter that the next token is exactly apartment, because if we do that exact kind of matching, it's more likely to introduce side effects. So it's creating this vocabulary where it's creating these areas that things are related in the latent space, and instead of changing the token to the exact next token, it's creating an anchoring for that, this anchor point, which is the center of these related tokens, and it's changing that center, the response to that center. I know this is a bit too high level, but that's a problem that I think is quite interesting also in the software engineering, where we have these models. And to go back to the quote that I got of that Gutter, how do we fix that model to not produce, those bugs anymore? And so we can use this kind of approaches where we edit the models directly to make them more reliable with less hallucinations and better. And so that's that work. So thank you very much. And I know it was a lot, but any questions, happy to answer.